Hi, I'm a student from Harmony School of Advancement, and in this video I will be explaining the relationship between linear mass density and wave speed. Wave speed on a string can be changed by changing the medium or tension. In this experiment, the medium will be changed through altering the linear mass density of the string. Linear mass density is defined as the amount of mass per unit length. The relation between linear mass density and wave speed will be modeled by this experiment. Our driving question: how does the linear mass density of a string affect the speed of a wave that travels through it? Our hypothesis: the equation velocity is equal to the square root of the force of tension over the mass of the string over the length of the string shows that as the linear mass density increases, the velocity will decrease exponentially. Knowing this, the string with a higher linear mass density will have less of a wave speed than the string that is more dense. If the linear mass density of a string is increased, then the speed of the wave that travels through the string will decrease exponentially because a heavier string does not allow a wave to travel through it as easily as a lighter one. The materials used in this experiment were 5 strings of different masses, a Pascal sine wave generator, a wave generator control panel, clamps, a rod, a pulley, masses, and cables and wires. The procedure we use in this experiment is written below. The data table shows that as linear mass density increases, wave speed decreases and frequency increases, with wavelength being held constant. The graph also shows that as linear mass density increases, wave speed decreases exponentially based on the curve of the graph. According to the data, the wave speed decreases exponentially as the linear mass density, the mass of the string divided by its length, increases. For the most dense strings, the frequency for the second harmonic was lower than those that have less dense strings. This is because each have the same wavelength and the velocities have to be different according to the equation. If the linear mass density is quadrupled, the speed of the wave on that string will be halved. The linear mass densities were 0.0046, 0.00146, 0.000914, 0.00056, and 0.00089. The wave speeds for those strings were 30.15, 49.05, 66, 83.55, and 75 respectively. There were some errors that could have made the values calculated by both equations be slightly different. These errors include not being exactly at the second harmonic, which means the frequency is slightly off. By collecting data regarding the wave speeds of strings with different linear mass densities, it was found that the linear mass density of a string decreases the wave speed exponentially when the level of harmonic and tension in the string are kept constant. It was also shown that wave speed is only dependent on the medium, which, for strings, can also be defined by its linear mass density. Therefore, each string had differing speeds at which waves traveled through. In the future, the tension of the string can be altered to determine its effect on the wave speed. Additionally, to make the experiment more precise, more data points can be taken to improve the graph's accuracy. This experiment can be applied to string instruments and the material used to make the string. To alter the sound quality of the instrument, a company can change the density of the string, which will best fit the wave speed they want to achieve. Our society can benefit from this discovery because instruments would not be how they are today without knowing the relation. Our social studies components and ELA components are shown below. Thank you for watching.